Hi, my name is Amani Smith, and this is my lab report for lab number 2. So, the purpose of this lab is to find the charge on a piece of tape using a model that represents the tape as a line of distributed charge. This differs from lab number 1, where we treated each piece of charge tape as a point charge. And to use this line of charge on a computational model, we're going to code it in GlowScript. And here's a quick preview of the results. So for lab number 1, we found that the charge was 7.7 times 10 to the negative 9 coulombs. And the charge that we found in this lab was 4.89 times 10 to the negative 9 coulombs. So the key physics principles used here were pretty much the same as in lab 1. We used Coulomb's electric force law, the electric field equation, and Newton's laws. The only difference in this lab, however, is the idea of superposition, where we sum individual point charges, little dq's, and treat each piece of tape as a rod. So here's a quick overview of lab 1, where we had two pieces of charged tape and balanced the top piece of tape using the electric force from the bottom piece. We found that the mass of each tape was 0.00015 kilograms, and that the length of each tape that we used was 0.15 meters. The distance at which the piece of tape began to move due to the electric force on the bottom tape was 0.019 meters. We calculated that the force acting from the bottom tape onto the top tape being balanced by the electric force and gravity was 1.47 times 10 to the negative 3 newtons. And we used this to find that the charge from the original lab 1 was 7.7 times 10 to the negative 9 coulombs. So a couple of assumptions were made during this lab. The first one was neglecting air resistance. And the second assumption, the main assumption, is that each piece of tape had an even distribution of charge. However, in actuality, some parts of the tape would have more clumps of charge than others. So here's the code for my computational model. You can see here that I start by defining constants k and gravity, the gravitational acceleration, and then we have the mass of the tape in kilograms. We have the estimated charge, 4.89 times 10 to the negative 9, and then here I define the electric field equation from lab 0. So this top function or code right here is to represent each piece of tape as tiny little point charges, or 20 point charges, n equals 20 to be exact, with the bottom tape position at the origin and the top tape position 0.019 meters above the bottom tape. And what this bottom function is doing right here, bottom code, is just calculating the electric field at each little point charge, or each dq. So here we have a visualization of the computational model with the green arrows representing the electric field generated by the bottom tape. And then we have the yellow arrow right here representing the force of gravity on the top tape, and then the white arrow over here bouncing the force of gravity, acting as the electric force due to the bottom tape right here onto the top tape. And you can see that the electric force and gravitational force are pretty close to each other numerically, and I got this by sort of doing a guess and check with my value q, which gave me a q value of 4.89 times 10 to the negative 9. So what if we used a point charge model, such as in lab 1, instead of a charge distribution model, such as in this lab? Well, you can see that the two values here differ greatly, and that the point charge model was a sort of overestimate compared to the charge distribution model. And the reason why these two values differ is because the line charge model is more accurate, and it's because of its precision. The more ends that you have, the more DQs, little point charges that you can represent the tape as, the more accurate of a Q value you're going to get. While the charge distribution model is more accurate, both models contain possible sources of error. We define the system as the two tapes and the force and the gravitational force due to Earth, neglecting any external forces such as air resistance. We also assume that both tapes were equal in charge, that they both had equal amounts of charge and equally distributed charges on their surfaces. We also didn't fully measure the mass of the tape. It was calculated using the linear density of tape.